I'm going to start and welcome everyone to our colloquium. This is a C3 AI Digital Transformation Institute colloquium series. And our mission, as you can see, is to attract the world's leading scientists to join in a coordinated and innovative effort to advance the digital transformation of business, government, and society. This is a group of universities and institutes, as well as industry. And we're very, very happy to be able to tell you about our upcoming talks. One on November 18th, Maria Laura de Monache, and on December 2nd, Kayu Guan. And these are talks that will continue the work that we've been doing so far in this area. We just are finishing today a workshop on the digital transformation of the built environment. And the talk you're going to be hearing about today is very much part of this research effort. So the past presentations are always available on our YouTube channel. And this format for our talks is there's a 40-minute presentation, and then there's a 15-minute period of Q&A. You should put your questions into the Q&A pipeline, and we'll get to them when we have time and in order in which they appear. And if you see a question or you just want to make a comment, you can also just put it in there. And you can also put your questions during the talk instead of waiting to the very end. So this colloquium on deep learning to replace, improve, and aid CFD analysis in the built environment applications is being given by Wei Lu, who is a new assistant professor in Sweden. He did his PhD at Purdue University. He's been tremendously productive. And you'll see from his presentation just how interesting his work is. And I'm delighted to introduce you to him. So Wei, it's your turn. Thank you very much.
Okay, thank you, Nari. Thank you, Tandy, for your introduction. So it is my great honor to be invited to this talk. So, okay, let me share my screen. Okay, so I believe now you can see my screen. Okay, so the topic today of my talk is learning to replace, improve or aid CFD analysis in built environment applications. As we know, nowadays, people in developed countries spend more than 90% of the time in the enclosed environment, and this enclosed environment include your offices, your home, and the transportation vehicles such as aircraft and cars and so on. Therefore, a somewhat comfortable and healthy and productive built environment is very important for the occupants. And such an environment is typically achieved by the HVAC system, that is the heating, ventilation, and air conditioning systems. So one reason that we need this HVAC system is the thermal comfort. So the thermal comfort zone defined by the ASHRAE is from 20 to 26 degrees C. However, our outdoor daily average temperature can range from, like at Purdue, it can be as low as -7 degrees C in the winter, and in the summer it can be 30 degrees C outside. And in Stockholm, where I stay now, the daily average temperature ranges from -4 degrees to 23 degrees C. So the indoor air temperature should be conditioned to the thermal comfort zone. And on the other hand, as to the indoor air quality, there are infectious disease, particles, CO2, VOC, as well as the particle transport from the outdoor to the indoor environment. So the HVAC system supplies the air to dilute or remove those contaminants. But even with the HVAC system, there are multiple problems in the current built environment. For example, this study shows that more than 40% of the non-smoking adults and 60% of the children aged from 3 to 11 years old are exposed to tobacco particles. And besides, 42% of the occupants are dissatisfied with the indoor thermal comfort in office buildings. So, and in the outdoor environments, there are also numbers of air pollutions, for example, the smog in developing countries and the overstandard emission from factories and the emergency, such as the forest fire and the terrorist attack. Even though people spend most of the time indoors, and those outdoor contaminants could be transported indoors through the ventilation system and the air infiltration. And besides, the transportation vehicles, such as the commercial aircraft, could be the carrier of infectious disease. For example, in this 2003 flight from Hong Kong to Beijing, and 20 among the 120 passengers were infected with SARS. And the index passenger is in the middle of the economy cabin, and the passengers 7 rows away are infected, and even the crew in the first class cabin. And during very short time, it spread to the 5 continents and 26 countries. And now we have the coronavirus, right? It emerged and rapidly spread throughout the world. And in Sweden, we have like basically 2 bursts of new infections. And now the 7-day average is about 500, and everything's back to normal. So with all above mentioned problems, when we doubt if we really spend sufficient effort or energy on the air conditioning, on the HVAC system in the built environment. So actually we do, if we look at the energy use, for example, in buildings in US, the total energy breakdown shows that 41% of the total energy is used by buildings. And further, the building energy breakdown tells us that the energy used by the HVAC system accounts for about 50% of the total energy consumption buildings in the United States. That is about $42 billion per year. So the percentage of building energy consumption in Europe is quite similar. So it is very critical for us to create a better or desired built environment with the minimum energy consumption. And my approach to this objective is the better design and control. So the better design is addressed by investigating how to supply the air to indoors, such as the air supply location, size, and parameters. And the control is addressed by the real-time control of the HVAC system, which involves in the interaction between the control algorithm and the fast evaluation of the ventilation performance. So all this need the accurate and also fast prediction of the built environment. And to model the built environment, the earliest method applies the analytical models and the empirical models. So the analytical one use simplifications in both the geometry and the small fluid boundary conditions to obtain a solution based on the fundamental equations of fluid mechanics and heat transfer. And the development of empirical models also adopt the data of experimental measurements or advanced computer simulations. So those 2 methods are effective cost-cutting tools, but they are kind of case-dependent, inaccurate, and not informative. And another way is the experimental measurements. Okay, we can use this to investigate the built environment. The left figure shows a small-scale church. So this is actually a church in Sweden, and we placed this small-scale one in the wind tunnel, and the experiment was to measure the pressure coefficient along the windows to further investigate the air infiltration in the historical buildings. And another study built this kind of full-scale cabin mock-up to investigate airflow in the aircraft cabin. So the experiment study are usually thought to be reliable, but they are often very expensive and time consuming. So the measurements are mainly used to provide data for validating the computer simulations. So the last way is the computer simulation. And previously we have this kind of multi-zone model that treats a room as a single load, so it can be very fast, but it cannot provide detailed flow information, such as air velocity, temperature. And it is not accurate for flow with strong temperature or momentum gradient. And on the other hand, we can solve the Navier-Stokes equations, and the computational fluid dynamics is more sophisticated and can perform detailed airflow simulation with high accuracy. So through the years, CFD has been widely and consistently used in the indoor environment to simulate the turbulent flow, heat transfer, the contaminant transport, as well as in the urban environment to simulate the wind around the buildings or at the pedestrian level and track the outdoor pollutants. For example, the CFD can be used for the indoor airflow distribution design. And in this animation, you can see the CFD tells how the air flows and how the air helps dispersing the indoor particles and maybe further mitigating them. And so here we have a particle source close to the diffuser, and the air clearly brings the particles to the seat far away from the source. And with airflow, the CFD also tells the temperature distribution, which could be used to evaluate the thermal comfort. And also, it is generally accepted that the infectious virus spread from person to person via small respiratory droplets. So these are generated when a person with the virus breathes, coughs, or sneezes. So the size of the droplets ranges from sub-micrometer to super-micrometer, and these exhaled particles can be transported in the air. Then one can contact the virus if you breathe in these droplets, which is typically called the person-to-person particle transport. The CFD could be used to investigate this kind of transport. And as you can see in those two animations, so when you cough, if you cover your cough by your elbow or tissue, it can greatly reduce the spread of the produced particles. And also, we know that the lateral ventilation can provide free cooling for buildings, but it is very difficult to design. So CFD is able to use the weather station from a suburb weather station, such as the wind speed and direction, to determine the airflow around the building. And the airflow around the building could be extended to the ventilation performance in an apartment in the building. And also the CFD could be used to identify the contaminant source in the enclosed environment, such as this aircraft cabin. So by using the sampled contaminant concentration from the sensor, the Navier-Stokes equation for the scalar transport was solved by setting the time step to be elective, and to make this equations stable and solvable, this study adopted a fourth order term to replace the diffusion term. Okay. So all above mentioned applications of CFD in the built environment requires many hours or tens of hours or even more computation time. So it is dependent on the turbulence model that they used, the numerical schemes, and the couple of the pressure and the velocity and the scale of the case and the computation resources that you have. But there are also many applications in the building industry that the fast airflow simulations are highly demanded. So in the building emergency management, like in a fire accident, the fast simulation of airflow movement and the smoke dispersion can help the rescuers make more effective smoke control strategies and evacuation plans. And the fast airflow simulations will be helpful, will also be helpful in increasing the performance of the energy simulation tools. And another, in the operation of the HVAC system, the regulation of the indoor air parameters requires suitable tools for predicting and controlling the air distribution in the buildings. And the air distribution predictions can provide crucial information about the IAQ, the indoor quality, and the thermal comfort level in a building or in a room, even before the building is constructed. So the control of the indoor quality and thermal comfort requires this kind of fast and real-time simulation of air distribution for the HVAC system operation. And also the faster airflow simulations can be a useful tool for architects to design buildings with sustainable technologies such as the lateral ventilation. So we require even faster CFD simulations, and also the CFD have the accuracy problems. As you know, the direct numerical simulation, it solves the Navier-Stokes equation and does not rely on any empirical fit. It requires extremely fine mesh and is able to capture the flow fluctuations. So although the DNS is conceptually simple, but it is extremely computational expensive and still infeasible on many applications. And then we have the large eddy simulation. So it solves the filtered Navier-Stokes equation. So it does not strongly dependent on the empirical fit because the filtered small eddies tend to be more homogeneous and universal. But so it is able to capture the major flow fluctuations. Comparing the LES with DNS, the computational effort is greatly reduced, but LES is still very expensive and out of reach for applications with large simulation domain. And then we have the RANS model that solves the time average Navier-Stokes equation. So it can only provide the average, the air velocity, or other properties and the deviations. The prediction accuracy is highly dependent on the exact RANS turbulence models that we use. It requires less mesh and it is and much less computing time. And also we have the hybrid model that it is to achieve both better accuracy and efficiency. So for example, the detached eddy simulation that applies the RANS model in the LEO region and the LES in the other regions. So, but the industry standard of low computational demand CFD analysis is still the RANS models. But the RANS equations are still high and nonlinear, and they introduce the so-called closure problem. So the closure problem is often given by modeling the Rayleigh stress using the Boussinesq eddy viscosity hypothesis that establishes a linear relationship between the Rayleigh stress and the mean strain rate. The eddy viscosity hypothesis is renowned to be physically wrong, but nevertheless used. Such an assumption further increases the uncertainty of the numerical simulation, which is another reason that none of the RANS turbulence models can ever be accurate for all range of flows. And these are the main of numerous uncertainties raised by CFD. And also, the problem with CFD simulations in built environment is that even with a small indoor domain, the airflow is quite complex. So it makes the RANS simulations especially demanding in the design process with numbers of scenarios. Okay, and but the RANS model is also not that fast with big computational domain. So in the previous studies, people tried to seek a balance point between the accuracy and the speed. So they investigate the intermediate models that can provide rich information as the CFD does with good accuracy, but it can be much more fast. So those intermediate models include, for example, the coarse grid CFD that neglects the impact of the grid resolution, but it cannot handle complex geometry. And also the coupled CFD, the multi-zone model, which is specifically used to predict the contaminant transport, and also the fast fluid dynamics. It can be tens of times faster than CFD, but it has the same or less accuracy than the RANS model. So it also has the accuracy problem. And then we have the deep learning, and we found that this by using the deep learning with CFD, it has a great potential to improve both the accuracy and efficiency. So in the built environment, the current research is only limited to the so-called surrogate modeling for fast simulations. So depending on the specific problem, the surrogate modeling can allow for orders of magnitudes faster airflow simulation and or even real-time prediction in some cases. So it solves like one of the two problems raised by the safety simulations. It can be very efficient. So even though the main objective of the surrogate modeling is to reduce the computational cost while keeping the same order of accuracy, the computational inexpensiveness usually comes at the cost of degraded accuracy. So surrogate modeling is often built from and compiled with the CFD simulations, which still present all the uncertainties stated before. And in the best cases, the surrogate model can produce very similar results in terms of accuracy with the CFD, but it can be pretty worse in the other cases. And also because of the inexpensiveness, the surrogate modeling is a major focus of the current research of built environment application. But there are certainly possible other ways to make use of the deep learning architecture. So for example, in the built environment applications, the surrogate modeling can be used to replace the CFD in predicting the built environment. And in this example, it used the deep learning models such as the MLP, the RF, or more as surrogate models to quantify the thermal comfort of the indoor vehicle cabins for different boundary conditions, like the air supply temperature, air supply velocity, humidity, and the glazing conditions. And to better assess the indoor thermal comfort, they study not only performed the equivalent temperature analysis, but also calculated the predicted mean volt. Since very fast predictions can be achieved, so we just use a kind of trial and error process for the design purpose. But of course, we can integrate the ANM model, the surrogate modeling with the optimization algorithm. For example, we can integrate the geological algorithm with the ANM method. So it is kind of very straightforward. We just replace the CFD by the trained ANN and compared with the pure geologic algorithm, we can reduce computational effort by like 65%. This is because it requires a lot of CFD simulations as a database for training the ANN. And we applied this kind of method to design the thermal comfort level, the air quality in the aircraft cabin. And as you can see in the right figure, this with the help of the ANN, we can greatly reduce the number of CFD simulations in the design process. And the upgrading from the scale of simulations from indoor to external environment, like the urban cities, the accuracy deterioration and the difficulties in considering complex boundary conditions, such as the weather, are inevitable. And in this study, they conducted the urban flow simulations where the location, dimension, and the shape of the 4 tall buildings were optimized in a restricted area with the construction of a CFD optimization tool. So the objective is to reduce the wind forces on buildings and mitigate local strong winds at the pedestrian level. So the focus of the study still resides on the CFD range simulations, which are eventually used to train a deep convolutional neural network for fast predictions. So they estimate that the CNN predictions could be about 50,000 times faster than the range modeling. So it is much more faster. However, the ANN predictions show lack of accuracy compared to CFD simulations, especially in specific cases that the network was not trained for, such as if we change the wind direction. Okay, so the method cannot be that accurate. So the surrogate modeling is an useful technique, and the main advantage resides in the possibility to obtain really fast and inexpensive predictions. And it also comes with the limitations such as being strongly case dependent and without good generalizability and in the lead of large training datasets. And in applying the deep learnings to CFD applications in fluid mechanics, there are actually 3 possibilities. We see it as the simple surrogate modeling. So here we see simple because it's just to replace the CFD with the ANN using the experiment data or high fidelity simulations to train the neural network. And we also have the POD and the ROMs, the reduced order models and the super resolution. So when it comes to the simple surrogate modeling, there are multiple works done primarily by the Guastoli, who applies the deep learning models to the extremely expensive open channel boundary layer DNS simulations. And it is one clear example of the computational efficiency advantage of the data-driven surrogate models over the brutal numerical simulations. So it can achieve very fast predictions, allow even real-time predictions. And when it comes to POD, the POD here means the proper orthogonal decomposition. It leverages the fact that the fluid flow pattern exists. Okay, so the POD is a standard technique that decomposes the flow in reduced order of orthogonal bases. So when you have this orthogonal bases, you can, with the different boundary conditions, you can reconstruct the flow field by those orthogonal bases. And in 2002, the Minano demonstrated that a linear ANN can do the equivalent of a linear POD. And the recent study focused on more advanced and nonlinear deep learning POD interactions for improved accuracy. And amongst the benefits that the data-driven model brought to the fluid mechanics research, the super resolution is a preeminent and new one for the analysis of fluid mechanics problems. So borrowed from computer vision and image recognition, the super resolution imaging refers to the class of techniques that aims at obtaining a high resolution image output from a low resolution image output. So the same concept could be applied to the flow fields by treating the flow fields as just an image. So the convolutional neural network are ideal and very good at this task. So using an offline database of high-resolution snapshots of flow field, for example, the DNS data as labeled output, it is possible to give input from the low-resolution data, either from the experimental measurements or from the coarse grid CFD simulations. So this method can consequently reconstruct the turbulent field to high resolution with the ANN. So in this oceanography study, the first figure is the test snapshot data, and the second one is derived from the sensor measurements as the input. And the last one is the reconstruct the high resolution output by the super resolution, and it agrees well with the first picture, that is the test data. And so these are the surrogate modeling that applied used in the fluid mechanics. And also in using the machine learning or deep learning for the CFD applications in fluid mechanics, some of the studies are not discarding the CFD numerical simulation, but making use of the data-driven machine learning models as an aid or for augmenting the turbulence models. So the deep learning techniques can be utilized in conjunction with the CFD simulations to increase the accuracy of the simulations. So what is often done is acting on the turbulence models that usually presents the highest degree of uncertainties. So in this approach, one treats the ANN models one trains the ANN models using the trusted data set that comes from the experiment data or even high fidelity simulations such as the DNS. So the DNS is expensive, but they run only once and used to train the network. Then the ANN will be fast in giving predictions at the end. And you can incorporate information about the physics of the problem, so which is kind of physically informed modeling in the ANN itself. And this is important if you want to conserve the physical information from the equation. And there are two possible ways to do so. And they are the tooling the coefficients of the turbulence model or the turbulence model enhancement. So as to the tuning coefficients, it is basically for the Rans turbulence models, because for the Rans turbulence models, the closure problem together with the eddy viscosity hypothesis introduce a number of constant coefficients varying from model to model. Those coefficients are determined from the combination of dimensional analysis and experimental measurements, usually in a simplified configuration. Therefore, Rans turbulence models are not universally capable for every flow, but actually depends on the specific flow features. So for a complex flow with multiple characteristics, the choosing standard values are a compromise. So a first obvious way to utilize deep learning algorithm on the turbulence model is for the constant tuning, finding for different flow applications the best values of the coefficients of a particular turbulence model. So such a method is not very generalizable though, and could possibly increase the uncertainties. So even though improving the turbulence model coefficients is extremely useful, the deep learning algorithm can actually achieve much more when interacting with the turbulence modeling. So their research is focusing on new ways of enhancing turbulence models by acting directly to the source of uncertainties, such as the closure modeling and the evident failings of the eddy viscosity hypothesis. And an idea is to use deep learning algorithm to build a representation of turbulence modeling closure terms. So it basically learns the behavior of the turbulence. Therefore, enhancing the model is more general and advanced, but complex approach. So this picture shows a specific tensor-based neural network, and its architecture is an example of physics-informed modeling because it conserves the physical property of the Galilean invariance, which is ultimately fundamental for the accuracy of the CFD solution. But there are still a lot of challenges. The first one is the extrapolation. So we already found that the ANN works the best at interpolation the data set. For example, as this figure shows, the grid area is the training data. Then if we want to calculate if we do some interpolation, then it works well. And if we take the test data as a future, so we need to extrapolate and give inference about the future. So it may not be that good. For example, in this oceanography study, the predicted flow, so they're doing the extrapolation, the predicted flow at when t is 20, which means the 20 snapshots. It's the predicted flow field still acceptable, but at the 50s, it's differed a lot from the test one. Okay, and in the built environment, it is also difficult and expensive to get the big amount of data for training the artificial neural network. There are some database online, but the information is still kind of limited. And how to involve the physics informed modeling is difficult to know sometimes. Okay, so in summary here, so the vast majority of applications in the built environment involves deep learning as surrogate modeling for faster predictions, which is justified by the expensiveness of the CFD simulations, especially in the design process. However, most often fast predictions comes at the cost of degraded accuracy, and the fluid mechanics research and applications in general offer inspiration for possible different interaction, which could benefit not only the prediction speed, but also the accurate performance. So above all, the physical informed deep learning modeling, the turbulence model enhancement with different techniques, and the super resolution techniques are the most promising methods that are not yet to be explored in the built environment for both the indoor and outdoor simulations. And we published a review paper on this topic at the Journal of Building and the Environment. So if you're interested, you can have a look at that. And with the support of the C3 AI, DTI, and the Digital Futures at Stockholm, we have founded a project entitled the AI-based prediction of the urban climate and its impact on the built environments. And the inspiration of this project is the urban climate determines the environmental quality in the urban areas by removing or dispersing airborne pollutants generated by human activities, through providing cleaner external or rural air. So study of the urban climate and its impact on the building environments would help provide guidelines and tools for urban planners and building engineers to evaluate the environmental quality in our living space. And given the practical difficulties of performing the city scale or multi-scale experiments, so accurate simulation, fast decision supporting tools are urgently in need to provide pollutant mitigation strategies. And the existing development of such tools have been plagued many three challenges, like the computational speed, the accuracy, and also the robustness. And in this study, we will develop AI-based CFD simulation to realize the accurate and fast prediction of urban climate and the built environment. So we will focus on two aspects in developing the models: the AI-based turbulence model by learning the behavior of the turbulence, that is a kind of enhanced method, and the AI-based surrogate model by using the super resolution and the convolutional neural network. And in order to train and test the ANN model, we will collect data, basically the experiment data from both the indoor and outdoor airflow from on-site or lab measurements. And we have three participants here, myself and the Professor Nikas Laversen from the Department of Computer Science at the BTH, and also he's a professor at the InCircuit University in Sweden. And we also have a PhD student who's Giovanni, who will mainly focus on this project. And we have some progress at the moment. So our current research is just starting, but we want to create a solid infrastructure of interactions between deep learning and CFD applications in the built environment. So we start with a zero equation model that is the simplest turbulence model, which directly computes the turbulent viscosity. So this relation is just very raw, but works okay for some flow field. So our first objective is to train the ANN that computes directly the turbulent viscosity as a function of the local air velocity and the Anand scale. Then we will it will replace the turbulence model of the CFD, and the mapping of the between the velocity and Anand scale and the turbulence viscosity is determined by the ANN. And to train the model, we start from an easy and inexpensive room CFD simulations with the RANS model, the RNG caps model, and get the data from there. And we used a very limited amount of points to get a fast idea of the work. And the red two figures shows the training and testing predictions. So once the ANN is trained, we implement it on a CFD solver, the open form, which is open source CFD platform. And we replace the turbulence model with it, and we run the simulation. So basically at every iteration of the solver, the solver needs to list the turbulence viscosity, which get computed by the ANN. And we used it to test the procedure and the algorithm on the same case, and we can see we can obtain the similar results as the CFD simulation, and the simulation time is kind of same at the moment. Okay. And in terms of the future work at this topic, because this is just a first step to obtain better interactions between CFD and deep learning, but it shows that approach is feasible, and it sets the infrastructure for future improvements, which we are currently working on. So we will not use the RANS, but use the higher fidelity CFD, like the DNS or LES or the experimental measurements, and we will use the bigger data size and to train the model and try the models on different flow cases. And instead of a simple relation between the turbulence viscosity and the velocity and the length scale, we will try more advanced turbulence models or get rid of this turbulence viscosity at all. And also we will try to use more advanced deep learning architectures. And besides, we are also very interested in trying the super resolution techniques applied to the grid concepts. For example, we can reconstruct the more accurate flow field computed by the very expensive fine grid by using a very low resolution coarse grid as the input. And we will also try to say if we can solve the extrapolation problems that we found in the other studies. Okay, so I think that is my presentation today, and I'm open to questions. Thank you.
Hey, that was great. So thank you so much. So for the audience, you can put your questions into the Q&A, and then we will answer them. So while we wait for people to put questions into the Q&A, let me just ask you something that I'm kind of curious about. So what are the other uses of deep learning or other types of machine learning for the built environment besides the CFD analysis?
Okay, so besides the CFD applications, actually there are already a lot of other applications, such as people directly use the deep learning framework to predict the indoor air quality and thermal comfort by using the climate data and the building information. And there are also people use the deep learning to train the control algorithm in controlling the HVAC systems. So there are many other applications available.
Great. So there's a question in the audience. It says, from Yu-Hu, it says, for the surrogate model, do you have a suggestion for what model can be used? And also, is this model explainable, not like ANN that is black box?
Mm-hmm. Yeah, so in our project, our plan is to try the super resolution, this kind of circuit model in our next step. But it is, I have to say, it is kind of black box, and also the POD one can also be a good option, but for the simple circuit model, it may not be that good because the generalizability is not so good.
Okay. Wondering if the audience wants to ask another question. Okay, well, let me ask another one of my own then. So I'm interested in like the speed. So how much faster is the AI-based CFD simulator than a traditional CFD simulator?
Yes, so in the review studies, so one study can achieve like 50,000 times faster than the traditional CFD. So that is much more faster. But in that one, they used as a kind of the convolutional neural network. So as a surrogate model, so it is kind of case dependent. But in the future, in the model development, as we know, in the building applications, we have the flow simulation, we have the energy simulation, we also have the climate simulation. So it is the best that we can have all those simulations at the same level of computational speed so that we can run all of them together.
Cool. Okay, so are there any other questions from the audience? Well, let me just ask you then one last question, which is, I think, more general. There's a lot of, real interest in seeing how far AI deep learning can go. And some people are very concerned about generalizability. Some people are not so concerned about it. What do you think is the biggest challenge for deep learning to really, really be useful? And what is your biggest concern?
It's really hard to say because for me myself, I have to say I'm kind of new to this area. So that's why I say in our project, we have a professor from computer science. So I have to say I'm not an expert on the machine learning. So I'm more kind of fluid side. So for us, I think the obstacle here is to get to know more about the deep learning itself and to make the best use of it.
So you know what? I'll ask you again in a year. we'll
Okay, thank you. Yeah, sure.
Okay, that sounds good.
Yeah.
Does anyone else, for example, do any of the panelists want to ask a question? No. Okay, well, thank you so much for your talk. It was really fun. And I hope that we will see you again at some point soon.
Yeah,
Thank
sure.
you.
Yeah,
Okay.
thank you.
Bye.
Yeah. Bye.